Hi everybody, welcome to the fifth lecture in the series of Tensorflow tutorials. And today we are going to be talking about how to manage your deep learning experiments. So when you are writing a model or coming up with a model, what you'll be doing is you're going to be trying various things. You're going to be starting and restarting the training. How do you manage all that is something we are going to be covering. And I might actually break up the lectures into various parts because I think it might make more sense to upload videos in bite-sized pieces where we are discussing one topic. And that way, hopefully, I'll be able to upload lectures more frequently. So let's get started. I guess the next lecture is on convolution neural networks. I'm pretty stoked to cover that when I get to that. So the agenda today is going to be, we are going to be discussing some ways to structure our programs. We are also going to look at tf.train.saveur, very important. And some other items for this whole lecture are the summary ops randomization of variables, of the variables when you start them, the readers. So let's keep on going. So deep learning is all about gradients, right? And when we are coding up our TensorFlow models, we are not really dealing with them directly. So where are the actual gradients? So what we get in a deep learning framework such as TensorFlow is we get automatic differentiation. And this is it's hard to stress how easy it makes things. And I just before this video, I had uploaded another video on backpropagation where I went into a lot of detail on how exactly backpropagation works and what the underlying system has to do to be able to give users such as yourself and me a very easy interface where we pretty much just have to write the forward pass. And if you have not done so, it might be a good idea to take a look at that lecture. And that would give you a deeper understanding on how backpropagation actually works under the hood. So, and we went into graphs such as this, where once we come up with a forward pass out here, the system is going to generate these backward passes for us. There is also an op which TensorFlow provides, which can allow us to find gradients of y with respect to each tensor in the list that is provided as the second argument. So basically, if we were to look at an example where we define a variable x, which is tf.variable and some initial value, and we have the value of y as 2 into x cubed and z as 3 plus y squared. And if we were to find the gradient of z, tf.gradients z comma xy, a list of tensors, what this will give you is dz by dx and dz by dy as a list. Okay, so and again, everything in TensorFlow, in deep learning, the way we are going to be doing things, everything is going to be numerical differentiation. So we will actually have a value for x when we get started. So when we define a session, as usual, this is an op, so we have to run the initializer for the variable. And now when we do a session.run grad z, we will get this value. And you can go ahead and convince yourself that if you were to take dz by dx, what you will have to do is first take dz by dy, which is going to give you 2y, and then multiply it by dy by dx, which is going to be 6x squared, and that's going to be the value of dz by dy. And when you put in the values of X and Y calculated at that point, you should see 768, and the same for when you calculate dz by dy, and you can just convince yourself that you'll get that. And in TensorFlow, you can get this pretty easily by just calling tf.gradients if need be. So the question is, should you still learn how to do this by hand? And I would suggest at least going through, if you're just starting on your deep learning journey, you would probably want to do this a few times, where you take some simple functions like sigmoid functions or some simple networks where you just have the affine layers, and you try to work out what the gradients are going to be. And the reason you want to do that is, again, as I talked about in the backpropagation video, you might run into situations where you have to write your own layers from scratch. And TensorFlow is definitely evolving. A lot of the stuff is already either given by the standard library, or people have been contributing different layers to the standard library, and it keeps on growing. So, but then there is a lot of research going on in deep learning, and there are certain things, for example, like we were recently involved with one of the projects where I needed to do object detection, and some of the most prevalent methods on object detection use a layer called a region of interest pooling, ROI layer, and that TensorFlow did not have. So we had to look into how we can write up that layer ourselves for doing that particular project. So this does come in handy. It's always a good idea to learn that. Also, depending on the network architecture, you might run into issues sometimes where the gradients either explode or vanish. So especially in plain vanilla recurrent neural networks, this can happen pretty quickly, where depending on where the weights initialization was, either the gradients just go through the roof, you get a NaN, not a number, in your program, and the program crashes, or the gradient just vanishes, in which case it fails to train, it fails to properly take into account the long-term dependencies. And having an insight into this might help you with coming up with alternate architectures, for example, LSTMs or residual networks, where this is less of an issue. So far, we have been using this one function in which we write our entire model, prediction, etc., etc. And one of the advantages with TensorFlow is, of course, we have access to Python, so we should be able to do better. And also, models, once written, we should be able to use them as needed. So one thing that you can do is kind of structure the model in a more object-oriented fashion. So you can have a function for creating placeholders, embeddings, losses, optimizers. And one of the things that I do is just move the model completely out. Let me show you what that means. So this is the way the assignments in CS244D, which was offered at Stanford a couple years back by Richard Socher. The assignments were structured like this, and I've been using that since that time, because this is very logical and it encapsulates things very nicely. So what you want is a base model called model, right? And this is the model from which everything that we'll be doing later we will be subclassing from. And what all do we have? We always need a way to go ahead and load data, right? And this just shows us the API, right? We will always, pretty much in a model, will be adding placeholders, and we will have an API for creating feed decks. We will Now, the add model part of things is where we are going to be writing the full inference. So basically, the output of this is the batch size and n classes. So this is the point at which we are actually doing the inference. It takes an input and it forward passes it, and this is the output out here. Then we have the adding of the loss op out here. The loss op is going to be returning a scalar. So this is the point at which it takes a prediction, right? And we already have the true output labels from the placeholders, and it will use this to create a loss, a scalar. It is going to be a number, right? And we have the API for running one epoch of the input data, and this we get a label to the session out here, and this will train the model for one epoch. Now all this is something, all these are things that we will always be doing, so it kind of makes sense to just abstract everything out as one base class. And then the final thing is fit, which is going to be calling run epochs many times, and it's going to fit, it will fit model on a provided data. We also have the API for a predict function, which takes in the session some input data and the input labels, and what it's going to give us is the average loss of the model and the predictions of the model on the input data. Now, if we were trying to learn a language model like the word to vec, etc., we would define a class language model, and the superclass is going to be model that we just talked about, and we are going to add one more method out there, which is the add embeddings, because that's exactly what you need. So now language model is the class that we can use for the word to vec skipgram model or something like that. So for example, if you were to come up with a named entity recognition, which was part of the assignment there, what you would do is you would have this config object where we are keeping all kind of config parameters like embedding size, batch size, label size, number of epochs, dropout, learning rate, etc., etc. Then we are going to create this class, which is the named entity recognition model, and we are going to subclass it from language model, because language model has that method for getting embeddings, and this is what we need out there. And all the other APIs like loading of data, etc., work the same way. So we have the add placeholders where we are adding the input placeholder labels and dropout. This is something we'll probably be talking about later. We have the create feed detect, where we are going to be creating the feed detect for inputting into the session. We have the add embedding method, where we are first creating the embeddings, and then we are going to be retrieving the embeddings of the particular window. Then we have the add model, which is the main forward pass for the neural network, and if you're doing skipgram model, that's where you're going to be having the forward pass. In this case, it's a one-layer neural network, slightly different. We have the add loss op, where we have the cross entropy in this case that we are defining, and the cross entropy mean. Add to collection losses, it's a different thing we'll talk about later. Here we add the training op, where we first instantiate an ADAM optimizer. In this case, we create the op, which is op.minimize loss, and then we return the training op. Now in the init of the function, what we are going to be doing is first getting the config, which is all the variables. We call self.load data, add placeholders, window self.add embedding where we initially create the variable matrix, and then we are getting that embeddings for one window of the input placeholders. That's our training X side of things. And we will get the predictions self.add model. We'll have the loss op, which is self.add loss op. This is where it gets all added into the graph. We have the predictions, and we have the training op, which also gets added to the graph at this point. Now we go ahead and run an epoch of training data, and what we have out here is we have a handle to the session for run epoch, and this is all part of the same API that we had created in model. We have the input data, labels, we always want to shuffle, by the way, and this is where we just go through the running of an epoch in a loop. Okay, and this is going to train the embedding matrices for one epoch of the training data. So hopefully this gives you an idea as to how you can structure your code so that you can run your models and write the code in a very nice modular way that is very reusable in the future. Now let's talk about how we manage our experiments. So when you come up with a deep learning model, you'll be running it multiple times, you will train for a while, you'll stop, change something, and will want to run again. And typically some of the models might take a long time to run, and you want a way that you start from the point where you left off. So there is this op that TensorFlow provides, which you'll be using all the time, tf.train.saveur. What that does is that it will save the variables in your graph in binary files. So it's not changing, it's not saving the model, though in TensorFlow release 11 onwards, even the graph is being saved. But in general, tf.train.saveur in this case is going to be saving the graph's variable. So as the model trains, the saveur allows you to snapshot those variables in binary files. So here's the definition of the method. You are going to be calling tf.train.saveur.save. You are going to be passing the session, because remember, the session is the entity which is encapsulating the entire runtime. It is the entity where all the variables are there. You're going to be providing a save path. So typically it's going to be of the order of some of the type some directory slash the model name, right? So if you're doing skipgram model, you will probably put out here some directory, let's say checkpoints slash, and obviously it's a string, so string checkpoints slash skipgram. And global step is a variable that you will provide, and if the value is, let's say, 59, then the file that this will get saved into would be skipgram-59. So this is because you want to be saving multiple checkpoints as the model keeps on training. So again, this is going to be saving the sessions, the variables. It's not saving the graphs in the earlier versions of TensorFlow. So this is an example of how you would go about actually doing it in code. So what you would do is you would create this saveur object, right? And now when we instantiate a session, and you will go into a loop of training, and in each training step, again, I'll reiterate, you want to call the initialization of all the variables, so which is missing out here. But you want to, for step in whatever the training steps, step.run optimizer, now the variables are changing, right? And if step +1 mod 1000 is true, probably because if this were just step mod 1000, then you will save even for the session 0, which so to avoid that, they're doing this probably. and you will call saveur.save session and some directory name, right? So in this, the actual directory name would be checkpoint underscore directory slash model name, right? And global step is equal to model dot global step in this case. So either you can say, for example, in this case, you could have even done global step is equal to just step, right? Because we already have a way to get a handle on the save. Now, this model dot global step, it is pretty popular to define a global step variable in your code. So this global step variable, what you can do is you can just have this defined in your model as just a variable self dot global step, and this is a tf dot variable, starts with 0. It's int 32. Important thing is it's not trainable. You do not want it to be trainable. You don't want backprop to run into that, because this is just a counter, and you will give it the name global step, or any name that you'd like. Now, what you would do is when you have, so you just define this as we just talked about, we have the global step. Now, when you define the training op, which is, I always like to call the tf.train.gradient descent optimizer, I like to call it that particular return as the self or dot optimizer. And when you actually do the dot minimize, I like to call it something like self dot train ops, so to distinguish between the actual optimizer and the actual training op. But we'll go with this. Here, the training op is self dot optimizer. And when you actually call the minimize, this is the self dot loss, that would be another op that we're calling. You provide this global step is equal to self dot global step. Now, what this will do is every time the training op is called, this will increment the self dot global step. So you don't have to worry about keeping the count, etc., etc. And actually, let's just go through the official documentation of Saveur class on TensorFlow docs. There are certain interesting things that I would like to pay attention to out here. So this is what we just talked about, which is saveur.save, and you are saving the session. And you'll give some directory name slash model name. So in this case, by default, the directory name and the directory is the current directory dot. Global step is equal to 0. So what you will end up saving is my model, which is here, dash 0. If global step were 1000, it would be my model dash 1000. And if this was under some directory checkpoint slash my model, so the file names inside that checkpoints directory would be this, right? Now, one of the other important things to keep in mind is this variable max to keep. So depending on your model, your variables can be huge. So I was recently training a model where the size of the variables file was huge in gigabytes, and it can fill up your disk pretty quickly. If you are doing this every 1000 steps or something, and you are running like hundreds of thousands of steps, this can be pretty expensive on your storage. So by default, if you do not provide max to keep value, then TensorFlow will, the value out here is 5. So it will only keep the 5 most recent checkpoints, which kind of makes sense. And then there is this other variable, which is keep checkpoint every an hour. So if you have a model which is running for days or weeks, you might want to just checkpoint every few hours. Let's say keep checkpoint every 2 hours or 4 hours. That way you have, you can later look into and get to any point within the training cycle. So that is another useful variable that can come in handy. And looking at one particular training example, so what we do is we go ahead and create a Saveur, and Again, you can provide a list. So if you don't provide anything out here, you will save all the variables. But you can also provide a list of variables. So let's say you have a variable such as v1 or v2, and the names are v1, v2. You have specified that. Now you can just provide the list of those names out there, or a dictionary. So you can either provide the tensors, or you can provide the names out there, and it will only save those variables. So typically, if you were to do transfer learning, then you would have you might be loading in a huge amount of variables, but actually fine tuning on only like a few layers. So just to save disk space and increase the throughput, you would typically only save those variables. And so the rest is what we already talked about. Define the session, run the training ops, and if the step size is this, you can give global step is equal to step. So here we have that example where we have these two variables, v1 and v2 tensors, which are variables, and names are v1, v2. And you can provide when you instantiate the Saveur object, you can pass in a list, which is the key values. The keys are the names, and the values are the various tensors, or you can just provide the tensors out here as the list. And now when you do the Saveur, it's going to go ahead and only save those variables. And of course, you have the corresponding restore op, where you can call saveur.restore into the session, and out here you would provide the name of the actual model. So this is the directory and name of the file, basically of the checkpoint file. So the model name was skipgram, and we had provided a global step equal to 99999. So the actual file that got saved, variable files that got saved in the checkpoints directory was this. So we just provide the full name out here, and it's going to restore the variables within this file into this session. Now, when you want to restore your variables, usually you want to restore the latest checkpoint, right? And there are a couple ways of doing that. One is this way, which is being shown in the slides, where you call this function tf.train.getCheckpointState, and you provide a directory name to the checkpoint, so wherever the checkpoint file is. And then you do this checkpoint if it is not none, and we get a path to the checkpoint path, then we restore that to the session. So this is the way, but there is a much cleaner way of doing this. So what you can do is to call this function, which is tf.train.latestCheckpoint. So, and you provide the same checkpoint directory, and you will check the return value of that. If it is none, then you do not have a checkpoint, right? So you will have to train from scratch. Now, if not, it will give you the actual full path to the latest checkpoint. So you are done. Now, once you have that full path, you can just do session.restore from saveur.restore session, that, right? So this I would use this from currently this is probably going to be the latest and the greatest to use. Let me show how we can save the graph also in TensorFlow 0.11 onwards. So right now, as you probably know, we are on TensorFlow 1.0, so it's a later release. So all the stuff that we are talking about is going to be valid. So let's say we have these two variables, W1 and W2, and we create these collections called var. So what add to collection, tf.add to collection, what it does, it creates this key value where this is the key and the value is a list. So for example, when we say add to collection vars, the first value of that list will be W. You call it again with the same key, W2. So now you have the key vars and the list W1, W2 out there in the graph. and we instantiate the Saveur and all default values. Now we have the session, and remember that you have to run the global variables initializer even though you're going to call the save right away. So this initialization always needs to be there. Now, when you do this save of the session, just the way we have been talking about in the last half an hour or so, what will happen is there is this other method called export metagraph that is going to be called. And in your directory, and in this case, it looks like they're just doing it in the current directory, you'll see a mymodel.meta. Now, this is a saved graph file. So now, let's say you do this once and like in a completely different process on a different machine, whatever, the only thing you have access to are these model files, mymodel.meta, and let's say we have the checkpoint file, which is also in the current scenario in the dot, and this will probably be my model because we have not provided any global step out there. So now let's say completely different. We don't have the graph, or up to now what we were talking is we still have the graph and we would want to restart the program because the power shut down or whatever, and so we still have the graph, and you go ahead and restore the variables. But now let's say completely different process, we don't have access to our graph, etc. We open up a session, right? Now we have a new Saveur which we import the metagraph, and this is the mymodel.meta that got saved out here, and we want to provide this file path to this API call. Now with this new Saveur, you call new Saveur.restore session, the session that we just started, and in this session now we will put in the variables. So now this session got bound to the graph out here, that initial graph, and now this session got initialized to the values, the variables that had been saved out there. And we also have access to, now we have all kinds of access. So we have the access to the vars which had gotten saved out here in either, and I'm not sure, well, it's probably going to get saved in the data file, not in the graph file. I might be mistaken on that, but nevertheless, once you do that, you can just call tf.getCollectionVars just so that you know what values we are talking about, w1, w2, and if you were to print it out, now you go ahead and call the session.runs on these tensors, because remember w1 and w2 are still tensors. You need to use the session.run to get their values, and you can print them. So basically this is in addition to what we just learned, where what we learned was we were just talking about saving and restoring variables of a graph, but in the current probably 1.0 0.11 release candidate onwards, the same function, you're not even changing the API, the saveur.save will also create those .meta files that are the graph definitions that you can import later and use. Okay, good. So with that, we come to the next topic, which is tf.summary. And what I'm going to do now is to just stop this video, and I'm going to talk about this topic in a separate video. Thanks a lot.